Here's some examples of problems about graphing functions. Problem 1. Graph the function f of x equals x to the fourth plus 4x cubed minus 1 and identify the important features. First of all, the domain of this function is the entire real line. This is because it's a polynomial that's defined everywhere. The next thing to check for is vertical asymptotes. There can't be any of these because the domain of f is all real numbers. And now we can do tests related to the first derivative. The first derivative is f prime of x equals 4x cubed plus 12x squared. Now we can rewrite this as x squared times x plus 3, and we have an extra factor of 4 out here. Since x squared is always going to be greater than or equal to 0, the sign of f prime depends on the sign of x plus 3. So f prime of x is going to be less than 0 when x plus 3 is less than 0, or when x is less than minus 3. Similarly, f prime of x is going to be greater than 0 when x is greater than minus 3. The one exception is that when x equals 0, x squared will be equal to 0. So f prime of x is equal to 0 at x equals 0, and then it's also equal to 0 at x equals minus 3. So this means that f is decreasing when x is less than minus 3, and when it reaches minus 3, we find a local minimum. Then it increases again until it gets to x equals 0, where the derivative is 0, and then it increases again up to infinity. This means that x equals 0 must be at an inflection point. We also know that this function takes the value minus 1 at x equals 0. So now we can sketch out a rough graph of this. It decreases down from here, and then we have a local minimum at minus 3 around here, and then it goes up and then reaches an inflection point at x equals 0, and then it continues to go up like this. Now let's take the second derivative to see if we can find any more inflection points and determine the concavity and convexity of this function. F double prime of x is equal to 12x squared plus 24x. If we write this as 12x times x plus 2, we see that f double prime of x is equal to 0 at x equals 0 and x equals minus 2. Now we can also see that 12x times x plus 2 can only be negative if x is between 0 and 2, because x and x plus 2 must have a different sign, or between 0 and minus 2. So f double prime of x is less than 0 when x is in the interval minus 2, 0, and it's greater than or equal to 0 everywhere else. So this tells us that from minus infinity up to minus 2, the function f is convex. Then from minus 2 to 0, it's concave, which means that minus 2 must be an inflection point. And then finally, from 0 up onto infinity, the function is convex again. So let's label what we found so far on our graph. First, we can see that f is decreasing down to this local minimum here. In fact, it's a global minimum. And this happens at x equals minus 3. Then we have two inflection points. One right around here at x equals minus 2. And finally, one right here at x equals 0. Now we already determined that the y value down here is y equals minus 1. But we have yet to find the zeros of this function. I won't go through the process here, but if you use Newton's method, then it's easy to see that this point here is roughly at x equals minus 4, and this point here is at about x equals 0.6. Let's label those as well. And finally, the only thing we haven't checked for yet is horizontal asymptotes. But since the function goes off to infinity at both x going to minus infinity and x going to infinity, there are no horizontal asymptotes. So this is our graph.